Hello, in this video I will explain geometric series for IB. Let's start with the definition. Sum of the terms of a geometric sequence is called geometric series. If there are finite number of terms in a geometric series, the sum can be found by a formula. So let's develop this formula with an example. We have this geometric sequence here, 2, 6, 18, 54 and so on, and we want to find the sum. So sum is this, 2 plus 6 plus 18 up to 1458. We can calculate this sum, but it takes quite a while. We can develop a method to find the sum easily. To do that, first we need the common ratio of the geometric sequence. So 2 to 6 here, 3 times, 6 to 18 again times 3 and times 3. So common ratio of this sequence is 3. I will use this common ratio to multiply this sum. So I will multiply every term by 3. So S will be 3S, 2 times 3 will be 6, and then 18 and so on. So I will rewrite the true sums like this. So 3S is this. Every term is multiplied by 3, as you can see. 2 times 3 is 6, 6 times 3 is 18 and so on here. So there is a reason I wrote it this way, because I want to subtract these two sums from each other. So if we subtract them, 3S minus S will be 2S, 2 sum. Here I will not subtract 6 minus 2, for I will write 4 here. Instead I will cancel 6 and 6 like this, because I'm going to subtract them anyway. 18 and 18 is gone, 54 is gone, and so on. So up to 1458. So in here what is left is 4374 and 2. So if I rewrite them here, 4374 minus 2. So 2S equals 4372. S will be 4372 divided by 2. So it is actually 2186. So this is a lot easier than add all the terms together. So let's generalize this method and find the formula. The general term, sum of n terms, will be given in your formula booklet, and the formula will look like this. Sn equals sum of n terms of a geometric sequence equals first term of the sequence times, in brackets we have common ratio to the power of n minus 1 over r minus 1. Or we can write the same formula, u1 times 1 minus rn, 1 minus r. Because this is a fraction, if we multiply two terms by negative 1, we will have this fraction. So it will not change the value, but the order of the terms will be changing. So in the formula booklet, you will be given both equations. And it says here r cannot be 1 because denominator cannot be 0. Because as soon as r is 1, 1 minus 1 is 0 and it will be undefined. That's why r cannot be 1. So let's prove this formula. Assume that this is a geometric sequence. u1 is the first term, u2 second term, u3 third term, and so on. We already know that nth term of a geometric sequence is this. Un equals u1 times r to the power of n minus 1. This is also in the formula booklet. This formula is important because we can write every term of the geometric sequence in terms of first term and the common ratio r. So this sequence can be written as u1 stays as u1. Instead of writing u2, we can say u1 times r by using this formula. Instead of writing u3, we can write u1 times r squared, u1 times r cubed, and final term can be written as u1 times r to the power of n minus 1. Remember, what we did with the example is we multiplied the whole sum by r, so I will apply the same method here. Sn is equal to u1 plus u1 times r plus u1 times r squared up to u1 times r to the power of n minus 1. So I multiplied the whole sum by the common ratio r, so it became r times Sn u1 becomes u1 times r, u1 times r becomes u1 times r squared, and final term will be u1 times r to the power of n instead of r to the power of n minus 1 because we multiplied it by r to the power of n. Just like in the example, I will subtract these two sums from each other. So r Sn is here on top, and underneath it we have Sn. And if we subtract them side by side, this is what will happen. We have on the left side Rsn minus Sn, just like here, Rsn minus Sn. And in here, u1 times r and u1 times r cancel each other. u1 times r squared and u1 times r squared cancel each other. r cubed, and finally these two terms are gone. So what is left is the final term here and first term here. So our subtraction will be equal to u1 times rn minus u1. In this equation, if we isolate Sn, we will find the sum formula. So Rsn minus Sn, u1, rn minus u1. And if we move Sn here and if we move the whole thing to the left side, so we will have this. Sn equals u1 times rn minus u1 divided by r minus 1. Because we have here common factor u1, we can actually write this expression in u1 brackets, u1 times rn minus 1 over r minus 1. So as I said before, this is a fraction, so this equation can be written as u1 1 minus rn over 1 minus r. And both of them are correct. So in the formula booklet, the formula will be given like this, and r is not equal to 1 because denominator cannot be 0. So let's look at an example. First term of a geometric sequence is 5, and the common ratio is 2. Find the sum of first 7 terms. So we will find the sum of 7 terms. So let's do it. We know that u1 equals 5 and common ratio equals 2. So this is our sum formula from the formula booklet. I will just substitute these values here. Sn equals u1 is 5 times 2 to the power of 7 because I'm looking for S7, and then minus 1 over 2 minus 1, and this is equal to 5 times, this is 128 minus 1 over 1, so this is 5 times 127, the result is 635. Next example, this time the question is given in sigma notation. Here, k from 1 to 5, 3 times 1 over 2 to the power of k. This is the expression in front of sigma notation is the general term of the sequence 3 times 1 over 2 to the power of k. So we want to find the sum of first 5 terms, because if we substitute 1, 2, 3 up to 5, we will have 5 terms. So we want to find actually S5. What is S5 here? So let's find it out. So first term will be U1. So if we substitute k equals 1 here, we will have 3 times 1 over 2 to the power of 1, which is 3 over 2. And if we substitute 2, we will have U2, this is U1, U2 equals 3 times 1 over 2 squared, which is 3 over 4. So 3 over 2 is the first term, 3 over 4 is the second term. We can say that common ratio is here 1 over 2. So we know the common ratio and we know the first term U1. Now we can use the S formula, sum formula. S5 equals 3 over 2 is our first term. This is 1 over 2 to the power of 5 minus 1 over 1 over 2 minus 1. So if we do the calculation, it becomes 93 over 32. Now we will talk about divergent and convergent series. If an infinite geometric series add up to a certain value, it is called convergent series. If it does not add up to a exact value, then it's called divergent series. You may think that there is no way an infinite series is add up to a certain value. It can happen only if the common ratio is between 1 and -1, if it is less than 1, because then the terms of the geometric series is getting smaller and smaller. So let's look at some examples here. Decide that are the following geometric series convergent or divergent. So I will start with the first one here. First term is 2 and common ratio is 3. So next term will be 6 and then 18 and then 54 and so on. So this is getting bigger and bigger and bigger. So if we add them up, it will get closer to infinity. It will not approach to a small value. So that's why the answer in here, part A, is divergent. This is a divergent series. Part B is a different series. 2 is the first term again, but next term will be half of it, so which means the next term is 1, and then 0.5, and then it will get smaller and smaller. So we can say that this is getting smaller and smaller, so this is a convergent series. If it is convergent, which value, exact value, it converges to? So if you look at the sum of one term is 2 because first term is 2. Sum of first two terms is 3. Sum of first three terms is 3.5. Sum of four terms is 3.75. Sum of first five terms is 3.875. 6 terms 3.9375. 7 terms 3.96875. And 10th term 3.99609. So as you can see, it approaches, actually converges to 4. So it's a convergent series and it converges to 4. So let's talk about convergent series. So we will talk about sum to infinity, because in that case we are able to calculate the exact value, which is sum to infinity. In the formula booklet, you will be given this infinity sum formula, first term over 1 minus r. This formula can only be used if the common ratio is less than 1. So it is an absolute value. The reason is it's actually greater than -1 and less than 1. In this range, it will always converge to an exact value. That's why if we have this common ratio, then we can use this formula. Otherwise, we cannot calculate sum to infinity because it will be divergent. So let's prove that. How do we get this formula? So I will select r as 0.5 and I will use the calculator. So this is our sum of n terms of a geometric series, and I am using a common ratio 0.5. So 0.5 to the power of x. I am using this part. So if I substitute 0.5 for r, this will be 0.5 to the power of n. So if I add infinity number of r's here, it will look like this. So 0.5 to the power of 1, if I add only one term, the answer will be 0.5 here. And powers of r, powers of 0.5 is actually getting smaller and smaller, as you can see. So 0.5 to the power of 5 is 0.03125. And if we continue to the powers, as you can see, 19th power, sum of first 19 terms, even it gets almost 0.0002. Which means at some point, this r to the power of n, 0.5 to the power of infinity, will approach to 0. Here, it will approach to 0. So, the formula becomes then this: Sn equals, or S infinity in that case, S infinity equals u1 times 0 minus 1 over r minus 1. So this is actually 0 minus 1 is negative 1, negative u1 over r minus 1, or we can write as u1 over 1 minus r. Both of them are correct. This is already given in the formula booklet in this format, u1 over 1 minus r, and this is the reason, because if r is between negative 1 and 1, it will be diminished when it approaches the infinity. Example, find the sum of the following geometric series. Part A, 45, 15, 5 and so on. So in part A, these are the terms of the geometric series. Since it is geometric, there has to be a common ratio. So if you look at the terms 45 to 15, 15 to 5, we can see that our common ratio is 1/3. And this is a decreasing geometric sequence, which means we can find sum of the infinity by using the infinity sum formula. So r is 1/3, first term is 45. Now if we substitute these values into the formula, S infinity formula equals 45 over 1 minus 1 over 3. Just quickly remember the formula, S infinity equals first term over 1 minus r. So first term 45, 1 minus 1/3. So if we do the operations here, 45 over 2/3, and the result will be 68.5. Part B, these are the terms, and if you look at the terms 1/3, negative 1/6, and 1 over 12. So 1 positive, 1 negative, 1 positive, which means the common ratio will be a negative number. So 1/3, 1/6 is actually times 1 over 2. So we can say that common ratio is negative 1 over 2. And u1 is 1/3. So we just need to substitute this into S infinity formula. So it is 1/3 u1 over 1 minus r, 1 minus minus 1 over 2. There is 2 minuses, it will become plus. So 1/3 over 1 plus 1 over 2. And it is 1/3 over 3 over 2. And the result will be 2 over 9. Exam type questions. The first three terms of an infinite geometric sequence are 48, 24 and 12. Write down the value of r. So we can easily find the common ratio r, which is equal to either 24 over 48 or 12 over 24. Either way, we have 1 over 2. This is part A. Since we have the common ratio and the first term 48, we can solve part B, which asks seventh term. We will use the nth term formula, u1 times r to the power of n minus 1. So un equals 48 times 1 over 2 to the power of n minus 1. Now let's substitute 7. So u7 equals 48 times 1 over 2 to the power of 6. And the result is 3/4 or 0.75. Part C asks sum to infinity. Since this is a decreasing geometric sequence, we can calculate the sum by using S infinity formula, which is u1 over 1 minus r. So first term is 48. We substitute r as well, 1 minus 1 over 2. So this is 48 over 1 over 2, and the result is 96. Exam type question. Consider the infinite geometric sequence 4000, negative 3200, 2560 and so on. In part A, we will find the common ratio. Because these numbers are big numbers, we need to use calculator. So part A, we can find the common ratio by dividing terms to each other. So if we divide all these terms, we will have the same common ratio, which is negative 0.8. We could see that common ratio is a negative number because terms are alternating, positive, positive and negative. So that's how we know it alternates. Part B asks u9. We need to use general term, nth term formula for geometric sequences. So u9 equals u1 times r to the power of 8. If we substitute 4000 times negative 0.8 to the power of 8, and our result is this, 671.089, Again, we need to use calculator. Part C asks find the sum to infinity. We will use the infinity sum formula u1 over 1 minus r equals 4000 over 1 minus 0.8. Again, negative, negative. Be careful about that. So 4000 over 1.8. We know that 1.8 can be written as 18 over 10. If we write that way, so our result will be 40,000 over 18, or as a decimal number, 2222.22. These slides are created with part of a digital textbook. Only some of the examples and questions appeared on the video. The book has 9 sections and covers number and algebra unit. The book is created with minimalist design language, easy to follow and easy on your eyes with its dark theme. This is an interactive textbook. Other than written explanations, every section has video tutorials. All you need to do is click on video boxes and start watching. At the end of every section, you will find exam type questions. These questions directly prepare you for IB exam. They have written solutions as well as video solutions. Solutions are prepared in detail to make your understanding easier. You can purchase the book through Apple Bookstore and it works on your iPhone, iPad and Mac. The link is available in the description below. Thank you for your support and I wish you a great success in your IB adventure. See you in the next video.